All right, now we're about to go into our last section of this unit, which I know you guys are excited, ready to jump up and down. We're going to go back to our old friend, our gases, and sort of talk a little bit more about them and how they behave. Again, starting off with our objectives. By the end of this section, students will be able to identify the factors that affect pressure of a gas, identify and explain the relationships between pressure, temperature, and volume, determine the values for pressure, volume, temperature, and number of moles based on the ideal gas law, and explain the differences between real and ideal gases. Most of you probably don't realize that there is a real difference, but as we continue to go through, we'll be able to make those things a little bit more clear. Now, there are three main factors that are going to affect gas pressure. The first of the three is going to be the amount of gas. If I have a lot of gas, then that usually will create a lot of pressure, regardless of the temperature of that gas. The second, the volume, the size of the container or whatever it is that we are conducting the experiment in. The larger it is, many times the least amount of collisions we'll have, the lower the pressure. Or the smaller the container is, the more chance we'll have those collisions necessary to interact and to see these variables brought out. And last but not least, looking at the temperature. If we have a higher temperature, the rate of the molecules is going to be much faster. They're going to have much more energy, therefore colliding more often. Lower temperatures, lower number of collisions, and less chance of a reaction or interaction that we're going to deal with. Now, to help us understand the relationships between these factors, we have several scientists that have sort of laid the groundwork for us. In class, we'll be doing some demonstrations to help you understand what's going on with each one, either videos or demonstrations that you'll be able to utilize. But the first one we're going to talk about is Boyle's Law. And basically, Robert Boyle, came up with a relationship through his studies that when the temperature remains constant or temperature stays the same regardless, that if pressure is exerted on the gas, the volume will decrease, or it says that it's an inverse relationship. Pressure goes up outside, volume goes down. Pressure outside goes down, the volume of the same gas will go up. Now, this relationship is actually going to be very, very helpful as we continue to go through and move towards our ideal gas law. So understanding these relationships is not just something random, but we're going to come to where it all plays a key role. Next, we come to Jacques Charles, Frenchman. Now, after his studies, Charles found out that when the pressure is held constant, the volume of a gas is directly proportional to the temperature of the gas. What's a nice way to say it? That if we leave the pressure where it is, we raise the temperature, the volume's going to go up. We don't have to worry about any other situations going on with that. But if I raise the temperature increases, the volume increases. Lower the temperature, the volume is going to decrease as well. Next, we have a man named Gail Essex, his law. Now, his law says that when volume is held constant, the pressure is directly related to the temperature. So, if I raise the temperature, the pressure is going to go up as well. This is going to be our sort of framework, and these relationships will shape how we'll see how the rest will behave and interact. Now, to complete calculations, what we can do is, or what has been come up with is, what's called the combined gas law. And this is basically scientists looking at these reactions, looking at these relationships, we're able to see that, okay, I can put all of these together to explain how a gas will perform or react if I change one or more of these variables. Now, we'll be utilizing this formula a lot to actually do the calculations. How it is normally written would be P1 V1 divided by T1. Our temperature at the beginning, pressure, volume, temperature at the beginning, is going to be equal to our pressure, volume, and temperature at the end. Now, it's been written this way with all the cross multiplication done ahead of time, because it tends to make it a little bit easier for people to work with and to remember what they're going to do and not to get confused too much. But this is, again, called the combined gas law. If there's a situation where something is missing, say you get to a question and it relates volume and temperature, but pressure isn't there, you have the opportunity to then assume that the pressure is going to be held constant. If the pressure is held constant, it's the same as crossing it out, and you will be able to proceed with the relationship as it is with just removing pressure, or the same thing for either of the other variables. Now, we come now to the ideal gas law, and we're looking at another piece that was introduced by Avogadro. We talked about him earlier in the year when we talked about the mole. Now, his actual experiments were usually with gases. And he had a hypothesis that said, if I put equal volume of gases into containers, equal volume containers at the same temperature and pressure, there should be the same number of molecules there. Based on this, we utilize now, or has been the development of what's called the ideal gas law. The formula we're going to use for that is going to be PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is called the universal gas constant. We'll talk a little bit more about that because there are two that we'll have to worry about, and T, which is the temperature in Kelvin. If you go back and you're trying to remember how we did the whole Kelvin scale, it's going to be back in section 2. So you want to go back and review the information as much as possible so that you don't miss out on that. Now, what's the whole thing behind ideal and real gases? Well, one of the things that scientists have noticed that if we are using real gases, there comes a point when the pressure is really high and the temperatures are really low that they actually will condense into a liquid. If we're studying this in terms of gases, this will be a problem for us. So we came up with looking at these interactions and looking at how they bounce out to what we call the assumptions that we're going to utilize for I blanked out for a second there, for what we're going to use for the kinetic molecular theory. Looking at the fact that we want those reactions to happen as fast as possible. When they bump into each other, that they're not going to transfer energy one to another, that their movement is random and at high speeds. With real gases, they'll eventually condense. But ideal gases, we want to be in that situation because they're not going to condense, they're going to continue to move. So, with real gases, we want to look at the fact that they will have different volumes, and they will also have attractive forces that play a part in determining which state they'll remain in. Whereas ideal gases are going to be those, again, we assume that there's no difference in the size of particle. We assume that they're moving at very, very high speeds in a random pattern. And last but not least, that their attractive forces have been nullified. We don't have to worry about them. The collisions are completely elastic, and we don't have to worry about it too much. I hope that this has been helpful for you. If there are any questions, please write them down. If you missed any material, please feel free to rewind, and then we'll utilize this for our discussion tomorrow in class. Have a great day, and can't wait to see you in class.